And now we're going to turn to the final speaker of the morning session. That's Bhoopesh Mishra. After a PhD in experimental physics from the University of Notre Dame, where he specialized in applications of synchrotron radiation, Bhoopesh turned to biogeochemistry with postdoctoral training in geosciences and biosciences at Princeton University and ANL. Currently, he is leading the Sustainable Molecular Processes Group in the Department of Chemical and Process Engineering at the University of Leeds in the UK. And the title of his talk is Discovering the Shades of Black in Carbon by Combining Soft and Hard X-ray Approaches. Okay, Bhoopesh, I think you're ready to go.
Thanks, Peter. Thank you for the very generous introduction. And I would also like to thank the entire organizing committee for giving me a chance to speak here. It's a really exciting forum. So yes, as Peter mentioned, that I'm going to talk about understanding carbon chemistry using soft and hard X-ray approaches. But before I do that, I'd like to start with paying some gratitude to NSF and especially the Low Temperature Geochemistry and Geobiology program. And I was actually trying to dig some slides from early 2000s, and here it is. I mean, I was able to do that. So there was a partnership between NSF and DOE in early 2000s to create environmental molecular science institutes. And the one at Notre Dame was actually fully funded by the Low Temperature Geochemistry and Geobiology program. And these are literally some slides I could dig from early 2000s. The scientific objective of the MC at Notre Dame was to determine the effects of bacteria, natural organic matter, and other nano and microscale particles on heavy metals. The reason I wanted to start from that is also because one of the key preliminary data that went into that proposal apparently was an application of synchrotron, as in cadmium XAFs, for showing the cadmium mining mechanism on bacterial surfaces, and carboxyl and phosphoryl groups were shown to be the dominant sites. Of course, by that time, the broader paradigm of interaction of heavy metals with bacteria was already recognized, and that was also part of that program. But as an MC fellow, what I contributed to this program, funded by Low Temperature Geochemistry and Geobiology, was the different kind of functional groups on bacteria that was responsible for cadmium binding, both across the pH envelope and also over an absorption isotherm. And what was actually considered a paradigm shift at the time was that my work was able to show that sulfhydryl binding was the most important and dominant binding at low metal concentrations, as opposed to the ones that were shown earlier, carboxyl and phosphoryl. And there was no contradiction in this finding, but rather it was recognize that if you conduct these experiments using, for example, cadmium as a proxy and use high enough metal loading, then you'll only see carboxyl and phosphoryl binding sites because they're only 5 to 10% sulfhydryl binding sites, and which is easily overshadowed by the more generic carboxyl phosphoryl sites once there is enough high enough metal loading. So of course, cadmium was used as a proxy to show this sulfhydryl binding at low concentrations. And then we used mercury as a proxy to understand the richness of those very many different kinds of thiol binding sites on bacterial surfaces. And finally, we closed the loop using zinc as a proxy, because we always thought that there's this abrupt transition from oxygen functional groups to sulfur functional groups, and there must be a missing link of amines. But the main problem, why again it was a technological challenge rather than anything else, we were not able to see amines, is because in the first shell it's very hard to determine or distinguish rather oxygen functional groups from nitrogen functional groups using XAFs. So we had to wait until the new kid, Herfty, as in hydrogen, using to show that indeed after sulfhydryl there's these amine sites, and finally carboxyl and phosphoryl, as you can see in this figure here. But also, as it was thought that there must also be an evolution of cell surface physiology over the growth curve. Zinc Herfty also helped us to show that in the exponential phase, there is more of malate and particularly histidine binding. But as it goes further into its tertiary phase, there is quite a bit of cysteine kind of binding. So now, fine. I mean, we closed this loop finally, and we were happy with that. But somebody in this audience here might ask me, is that why were you using such indirect probes? Why use proxies when you can actually directly determine these? Why not use carbon, nitrogen, oxygen, XRS or STXM for direct measurements, or rather use soft X-rays rather than hard X-rays? And that's sort of what I wanted to talk about mainly. Now, the answer to that question can be complicated, depends on who you talk to. And I can say something like, well, NextApps and XTXM are great tools for speciation of flow Z elements. Advanced sample preparation, for example, microtoming or fifth sectioning is required. And also there's limitations in terms of sample environment in which you can use these techniques. Finally, the quantification of a species is usually complicated with soft X-ray techniques. By saying that, I'm not trying to discard or say that soft X-rays are not important, or rather the contrary, which we'll see in examples later. But let me prove my point by giving you an extreme example where there is a physically protected organic matter in a given sample. There's no way soft X-rays can actually reach these organic matter because one has to probe through the physical protection of, let's say, mineral before we can excite those from, let's say, the organic matter, the carbon, for example, in this case. And the reason for that is that for carbon, which is what I'm going to talk about mainly, is the excitation energy only 280 or 290 EV, which is really low energy, and the penetration depth is much lower. Similarly, if one wants to try to understand the carbon within a soil aggregate, inside a soil aggregate, there's no way of doing that because of the limitations of penetration depth and so on. So some of the advantage of hard X-rays is, of course, large penetration depth due to high energy, of course, and hence it can go through, it can punch through soil aggregates or any thick samples. It can also look through physically protected organic matter or hydrated samples under ambient conditions. And also, as mentioned, it can overcome sulfur absorption issues for better quantification of species. However, soft X-rays, of course, have its own advantages, and heterogeneity is one of the main ones because it has high energy and spatial resolution. It also has higher sensitivity and more appropriate for probing soft interfaces. It's faster measurement. So really, it's the combination of the soft and hard X-ray approaches that should be the key. Now, one of the hard X-ray technique that I've started using for, and as the schematic on the left shows, we use roughly 10 kilo-electron volt instead of 280 electron volts for exciting carbon. And this is a very indirect way of probing carbon, basically. And what happens is that you input very high, like hard X-ray energies, let's say 10 kV. And then what you do is that you measure the energy loss, and the scattered photons go and first get scattered with crystal analyzers, and then the energy loss is plotted, and that should give you the same spectra as NextApps, as long as we remain in the limit of low Q, as in low momentum transfer, because it has been shown mathematically that XApps and Raman essentially should provide the same spectra as long as the low Q momentum transfer is maintained. The main advantage again here is that X-ray scattering has 3 orders of magnitude higher penetration depth. For example, if you use 10 kV instead of 280 eV. So the schematic of X-ray Raman scattering works as storage in monochromator and so on. And then finally, sample, the light is shown at the sample, which goes and strikes to one of these crystal analyzers, scattering the scattered photons, and then they're ultimately collected by detector, and the energy loss is plotted. This is schematic of how it is done at APS in sector 20. And ESRF has actually a really neat system where they have a huge goniometer with 6 arms of detectors, and each arm has 12 detectors in itself. So there's a total of 72. And the main advantage and beauty of the system at ESRF is also that you can place these arms at whatever Q or scattering direction that you want to that you choose to do so. So these are the 2 main facilities, but there's also one at SSRL and few other worldwide. This is still a bit of a limited technique, and I'll show you some results coming from that. But before we do that, let's try to understand what's the main difference between XRF and XRS. So, of course, for example, NextApps has large signals and is surface sensitive primarily, but it needs to be done under special environments. XRS on the other side is a bit of saturation free from self-absorption effects, and etc. And a complex environment, sample environment can be constrained, can be used for this. But ultimately, this energy loss technique should give the same spectrum as NextApps, as I was trying to say. However, that's not always the case, as we'll see, because we can unleash the power of different techniques. And before I prove my point, let's go and see how XTXM works, and very quickly. So in case of XTXM, which is not only soft X-ray technique, but also a scanning technique, is that there's raster scans that are done through sample. And while doing these raster scans, we not only get images at each energy, but also we have a stack scan, which is very similar to what NextApps can provide, except it has also a spatial resolution of, say, 20 to 30 nanometer. So when we try to get different, when we try to combine these techniques, we get different answers, and which is nothing wrong with that. We just get a thin section of a soil aggregate, and this thin section provided us a different kind of, I'm just showing one spectrum where, which is representative of many kind of many different spectra that we had at different spots. And also NextApps gave a different signature. Finally, XRS also gave a different signature. So one can be confused, and one could be looking at, one could be asking that which one of these is right. So it turns out that we think that all of them are correct. So what is happening is that what XTXM is providing us is information about carbon locked inside the soil aggregate, which has never seen ambient conditions, and hence we see mostly abundance of aromatic and aryl moieties. Well, what XRS shows is the average of overall carbon budget, and that shows abundance of carboxyl groups. And so clearly, the physically protected carbon inside the soil aggregate appears to be less weathered than the overall carbon budget. Now, this finding should not surprise anyone, but indeed, this is a really neat experiment that we're able to conduct and get this answer. Have is that what kind of sensitivity these have. So for this soil sample, the carbon content was only 3%, hence it was very challenging for X-ray Raman scattering. And we had to spend a considerable amount of time to be able to get these spectra that you see on the left here, and which still don't look like the best kind of spectrum that you can get. On the other hand, this was really fast for NextApps or XTXM. So those are the advantages that they have. Now, one can say that, okay, I mean, in this case, yes, it's a really complicated sample. What if you did something wrong and you are getting these different answers? Because we appreciate that, those concerns. And here's something that I'm going to show you based purely on lab created material. But before I go ahead and do that, let me remind you that 285 EV is the aromatic carbon peak. And there is also graphite-like resonance, as you see in this figure on the left. So we conducted both XRS and NECTAFs on hydrothermal carbon materials, which was lab created, and you see this huge difference in the aromatic peak of the same material using two different techniques. So it clearly shows us that the surface of the hydrothermal carbon is much more aromatic than the entire bulk or the overall carbon budget of these materials. Similarly, when we did this NECTAFs versus XRS studies on biochars at different temperatures, we also saw that at 650 degrees Celsius, biochar is not only much more turbostatic and aromatic in the bulk, but also at 400 degrees Celsius, the aromaticity of biochar is roughly the same as bulk, but again, the graphitic component increases with temperature. So with these examples, what I'm trying to show is that we can probe different properties, or we can probe different dimensions of the same material by using different techniques. And by combining these different techniques, we come to understand the material from different perspectives. And that's what provides such a powerful way of doing that. So not only that, when we further did XRS analysis of the hydrothermal carbon by again doing fib sectioning of that, as in focused ion beam sectioning of that, we could show the core versus shell model of this, which is something that was suspected for a long time, but was never proven, because what happens is that if you conduct XPS on this material, and there are ways of, there are smart ways of removing the upper surfaces in the shell material and then just measuring the core and so on. The carbon to oxygen ratio remains the same in this material by XPS, but the way they bind in the shell versus the core is different. And you can see this stack scan from the core versus the shell, and you can clearly see the difference in the peak ratio of the first two peaks for the core and the shell. So using this, we were able to construct the formation mechanism of HTC, which is something that was missing for a long time. And we concluded that aliphatic or carboxyl linking units join polyfuranic domains at the surface, while the linking units are removed in the core, leaving condensed polyfuranic domains. So this is something again that was really neat work, and it was a technological challenge that this community had never done, or was not aware of things like STXM, and STXM was able to provide really good answers. So in nutshell, what I'm trying to show you is that the kind of work that I'm doing now is we start with bio-waste, agricultural bio-waste particularly, and then we try to use these for different applications by carbonizing them. And essentially, I'm trying to understand the geochemistry of these, whether there's a complexation reaction happening on the surface of these carbons, whether that is inner shell or outer shell, for example, whether there are redox transformations that are happening or precipitation that is happening, and so on. And for that, a combination of different kind of techniques are needed. For example, to understand the surface versus interface, we again have been using NECTAFs and XTXM. But to understand the bulk structure, of course, XAS is a very potent technique, but also for carbon, XRS has become a very, very useful. And not just carbon, it can also be done for nitrogen and oxygen. It's just that we have focused more on carbon. And for understanding the morphology, microtomography is something that we conduct a lot. So to summarize, we start with lignocellulosic bio-waste, for example. Rice husk is an example, or spent coffee grounds is another example. And then we conduct XRS to understand the formation mechanisms, in which in that process, we also try to make these more potent material by doping different kind of ligands, like including sulfur and nitrogen. Nitrogen doping has been shown to have different properties, including higher energy storage properties. And then we functionalize these with nanomaterials. Now, this is just a difference in the terminology. When I say functionalizing nanomaterials, what I mean is that we incorporate minerals, nanoparticulate minerals, manganese and iron oxides, which is something that have been very dear to us geochemists. And for that, nucleation sites are probed using STXM and sometimes NICSAFs, and functionalized nanocomposites are formed, which have catalytic properties. Cross-shell hydrogel beads serve as advanced sorbents and so on. And again, I mean, in situ XFs and is used to understand the properties at each step. But also another important factor which was missing, or rather something that could not be done in natural systems and which could be done in these engineered materials, is tuning the porosity. So we can use different techniques to try to create hierarchical porous structure of these carbon materials. And that is something that we routinely probe using tomography. That's something that I'm not showing here. So I'll give just one example of what we have been doing, because I don't want to take too much of the time. I don't want to stand before lunch and you guys. So this is a manganese oxide biochar composite. And while one can say that, okay, what's the big deal, in the sense that manganese oxides are really easy to form, which is indeed true. But forming true manganese oxide biochar composites are not straightforward, because carbon itself, in this case biochar, has its own electron shuttles and so on. So we have been able to do that after 2 years of failure, and finally we have what is truly manganese oxide biochar nanocomposite, and you can see some of these high resolution TEM images in this for the surface particles, and we conducted these experiments for different kind of feedstocks. In this case, oak wood at two different temperatures, 450 and 650, and also rice husk. And we tried to understand using Zane's linear combination fitting is that what's the bulk, what is the ratio of different kind of manganese in this system. And of course it is mostly manganese 4, but that's not enough for us to understand this material, which is also we have tried to understand the carbon chemistry of using XRS and also tune the porosity and so on. But finally, it is important to understand that what kind of manganese oxides are there, and it turned out that the highest performance material for removing a different kind of contaminants from water was the one oak wood at 650, because it formed triclinic bernstein and also MnO2, and together they're providing both catalytic as well as high absorbent characteristics. So with that, I'm going to sort of wrap up my talk, and I hope that I was able to show that how we can combine very many different techniques to understand the same material from different angles, and hence construct something that is highly useful in terms of understanding their property function relationships. And of course, I have a lot of people to thank to here, including my mentors and collaborators over years. A special mention to Sarah Thomas, who was the postdoc with Satish at that time, who did the HRFT work that I presented today. And also to my postdoc and PhD students who should really be the one talking, but I'm talking instead of them. Thank you very much. I'm happy to have questions if you have any.
All right, well, thank you so much, Bhoopesh. You do have a couple questions. Song Su asked, I've been curious about whether we will be able to obtain the same level of atomistic information from inelastic X-ray scattering, such as LERIX, as we do using XFs. Can you make a comment about this issue? Did you catch that?
Sorry, I'm trying to, okay, let me stop share first and then go to, okay.
So he's asking whether you can obtain the same level of atomistic information.
Same level of atomistic information from elastic. Yes, okay, right. Right. Yes and no, in the sense that if you are probing a system which is concentrated enough, if you're talking about solid samples, and if it is we are talking in the range of few percent, like maybe 10% and above, then of course there's a very good chance that you'll be able to have a lot of information. But also the energy resolution, at least for carbon, we have seen is not a problem, and we are able to have very similar peaks all along in terms of energy resolution. Does not come as a handicap for carbon, at least, but it's possible that for some certain other elements that could be a problem. So it needs to be seen. But if you are trying to do this in solution, which is also something we have done, but that was for a different system, so I didn't present, we had to be in 1 molar level rather than millimolar. So it depends on what system you're probing and what kind of concentrations we're talking about.
Okay, maybe you can give a quick answer to Satish's question. What is the minimum carbon concentration needed to get a decent XRS of a sample?
I'm going to give a politically correct answer for that, in the sense that it depends on sample matrix. If there's a lot of mineral in the system, or rather high absorption material, then of course the sensitivity has to be not so good. And it is also a very photon hungry experiment. So if this experiment is being conducted at the system at ESRF, for example, we were able to go down to 2 to 3% carbon, and that had a decent amount of mineral content. Now, if you want to take it down to 1% or below, then if the sample is largely free from minerals, then yes, that's possible, I guess. Or on the other hand, like all these highly brilliant sources that we're coming up with each upgrade, it is definitely possible that in future, not so long in the future, but sometime soon, we should be able to do like 1% or so. But right now, I think we're limited to 3 to 5%. So it was really difficult to get that 3% level concentration for us.
Okay, well, thank you very much for that talk, Bhoopesh.